Hi, I'm Bow-Yaw from Sinica. I'm presenting our work on cell specification for RISC-V P-extension. This joint work. Hi, I'm Bow-Yaw from Sinica. I'm presenting our work on cell specification for RISC-V P-extension. This joint work with ND's Technology and National Tsinghua University. Hi, I'm Bow-Yaw from Sinica. Hi, I'm Bow-Yaw from Sinica. I'm presenting our work on cell specification for RISC-V P-extension. It's a joint work with ND's Technology and National Tsinghua University in Taiwan. RISC-V P-extension is designed for efficiency for small volume data parallel computation, and it has lots of instructions specially designed for signal pre and post processing, like rounding and saturation computation. And there are lots of activities in RVP ecosystem. For example, we have compilers designed for RVP, and also special digital signal processing library and neural network libraries for RVP, and also all support for RP as well. In terms of performance, RVP in signal process does perform better than RISC-V baseline instructions, and here are some experimental results from RVP versus RISC-V baseline instructions, and we can see it can be as large as 14 times better than baseline RISC-V instructions. And CEL is a sophisticated language for instruction set architecture semantics. And actually, RISC-V baseline instructions have been specified in CEL, and there's open source repository, CEL repository for RISC-V specification. And for RVP notification, every RVP instructions needs to be specified in CEL. It sounds easy, but the problem is there are 325 instructions defined in RVP. How do we write so many CEL specification? So in this talk, I will show what CEL specification look like, and also I will explain how to specify 325 RVP instructions quickly in CEL. We also discuss how to validate our CEL specification. Finally, I'll share out some of our experiences in writing CEL specifications. And here is an example of CEL specification for an instruction. In any CEL specification, we start with abstract syntax. So here we define R type is an abstract syntax. It takes 4 arguments, 3 register indices, and 1 OP code. And then after abstract syntax, we need to tell CEL how to decode and encode binary codes. And there's a binary encoder and decoder specified in CEL. So basically, it tells us how to extract register indices from binary code. And after that, we need to say how to interpret binary code with, or print binary code in assembly mnemonics. So here is how we translate RISC-V add instruction into ADD string, and also how to place source registers and destination registers. And finally, we are going to tell CEL what's the definition of this particular instruction. So here, ADD simply just add the content of 2 source registers. Okay, so everything looks fine. And now the question is, in RVP, we have more than 300 new instructions, and every instruction needs to have abstract syntax, binary decoder, encoder, assembly mnemonics, and also semantic functions. And how do we do that correctly? So our first idea is to automate. So in RISC-V RP codes repository contains basically a human-readable binary encoder and decoder. So here we can see 3 instructions, ADD8, 16, and ADD64, and basically tells how to encode these binary instructions. So what we do is we write a tool to convert all these human readable text file OP codes into cell specifications. Our tool can generate abstract syntax, and also will generate binary encoder decoder specifications and assembly printouts, and also semantic function templates. So in the 8 instruction example we see a few slides ago, so the gray area are now automatic. So for RVP instructions, we need only to write semantic functions for RVP instructions. Still, there are 325 semantic functions. And how do we do that? Very quickly. So let's take shift instructions in RVP as an example. So here we can see that RVP provides shift right, shift left, and also both ways shift instructions. And also there are basic shift instructions like shift, arithmetic shift, or logical shift. And also there are some special shift instruction for signal processing, for example, rounding or saturated shift instructions. And also there are different shift instructions for different bit lengths, 8 bits, 16 bits, or 32 bits. Hence, there are about 45 shifting instructions in RVP. So what we do is we try to classify all these instructions and try to identify the basic operations among these shift instructions. So what we can see is the shift instructions is divided by bit length or shift directions, and also whether it's basic shifting or rounding saturated shifting instructions. Because based on this classification, we write a cell function for each classification. For example, consider arithmetic right shift function, and in this case, we classify by bit length. So in the code here, we write a very simple shift right arithmetic function called shift right iris, and the input can only be 8-bit, 16-bit, or 32 bits. So this function basically tells us out if we want to do a right shift, arithmetic right shift for a 16 or 32 bit, just call this function. Okay, so you have 8 of such basic cell functions, and then with different combinations of these 8 functions, we can specify 45 RVP shift instructions very easily. Okay, so cell does provide more basic data types. For example, the bit vector can be, a more free bit length. Okay, so in restricted only to 16 or 32 bits, we can have 128 bits bit vectors, and also their operations. And also in cell, we can specify the input and output bit length more easily using its type system. For example, we can say if we get 8-bit input, and then we can the output of this function can be 16-bit or 8-bit bit vectors. And also type checking mechanism in cell is also very useful. This will check our specification at runtimes. For example, say the input and output bit length don't match, and then the cell compiler will say, well, there's an error here because this function is supposed to get 8-bit input, but we provide, say, 9-bit input. So that's an error. Okay. So with cell, and also with this classification, we can specify 385 semantic function really quickly. Now, the problem is they are still written manually, okay, and humans make errors. So how do we know our cell specifications are actually correct? So the truth is we actually don't know, because the bottom line is our cell spec must be the same as the RVP spec, and it takes time to examine them or to compare them one by one. Okay. Now, before that, can we do better? Okay. So before we compare each and every specification in RVP, can we detect errors, very quickly after we write our semantic functions. So we actually developed a technique to validate our specifications. So idea is we use simulator spike to get answers for each instruction, and then we compare the answers with our specification. Okay, so the idea is we generate random test cases, and then we get this the result from spike. Okay, and then we use cell emulator to compute the result of these random cases, and if they are the same as spike result, then it's fine. Probably in this test case, we're good. Otherwise, we know there's something, either spike simulator is wrong or our specification is incorrect. And then we use RISC-V test format. So this is the flow of our instruction level test case. So we generate random test input, and then we fed that input into spike, and then get the result from spike. And then we generate RISC-V test cases. After that, we compile it into the RVP binary, and then send that to cell emulator, and then compare the result of cell emulator and result with spike. So here's a running example. So first, we need to generate random tests. So this we can see that sort of random inputs generate from a simple script for RISC-V 8. And then we have another code which will extract spike results from these random inputs, and then put that into RISC-V test format. And then we compile these RISC-V test cases into binary, and then execute this binary in CLC emulator. So this is an example run of the code. So if it prints out success, which means that all the test cases are successful, means that the CLC emulator generates the same result as in spike simulator. And of course, spike simulator is just a comparison. So everything needs to be compared with RVP spec. Now this is just a validation process in order to help us to detect any errors in our specification. So in addition to RISC-V test cases, we also have a flow for RISC-V. In order to use RISC-V to test our specification, we need to have RVP support in RISC-V. And for that, they are repository for this configuration file for RISC-V. We get this RISC-V configuration file for RVP, and then we run our CL specification for RVP. And as we can see, that's for different instruction, so the results are passed. Okay, so that's second test we built for this RVP CL specification. And then finally, we want to do more heavy duty tests with our CL specification. And in this case, we want to test our specification with convolution computation in TVM. So we took the TVM-IR and then scheduled it into SIMD computation with RVP instructions. Okay. And in this implementation, the SmartCar instruction is used heavily, and this is our goal. So we want to test this RVP instruction as a group and then see whether any flags or any inconsistency between our specification. So SmartCar is a sort of very complicated RVP instruction. It takes 3 inputs. So RS1 and RS2 are 2 source registers, and each 64-bit register will contains 8-bit numbers. And in this case, SmartCar will multiply these 8 8-bit value pairs perform side multiplication, and then add 4 of these pairs into a 32-bit number, and then add that 32-bit number with the content of the destination register, and then put the result into destination register. So as we can see, this is not the typical computation one will use for every RISC-V task. This is what widely used in convolution. So we have this SmartCar instruction specified in cell, and then we basically use a C macro to have this RVP instructions to perform one phase of this convolution, and then we compare this into binary and use cell C emulator to run it to test this binary. Okay. So far, I've shown you how cell spec looks like and how we write this cell spec, and also how do we test 325 cell specification. So actually, cell is pretty good as far as we can see, but there's still something which could make cell better. For example, in our early specification, we find that the number of abstract syntax actually is limited. Okay, it's very limited. There can only be 246 abstract syntax trees. If more than that, then there's a compile error from OCaml compiler. So which means that as the number of extension increases, the type of abstract syntax will also increase, and we expect this 246 abstract syntax type will be running out very quickly. So if we are not very careful about how to define this abstract syntax, so that's one bad thing. We sort of try to minimize our abstract syntax type to avoid this problem. And also during our test case, it's probably easy to test instruction by instruction. As we can see, we use RISC-V and also RISC-V test cases. But when we want to do some serious testing, like convolution, we find that cell C emulator does not execute compiled C code. And this also goes with all the C libraries, like digital signal process or neural network libraries. They're all C code and compiling to binary, but then cell could not simulate this compiled C code. So which means that it's very hard to perform large-scale testing, like convolution or some DSP libraries. And if cell could add some support for these compiled C binary codes, I think that would be much easier for our large-scale testing. And then I want to say something about how our work can be applied to other extensions. So all the automation process, including translate RISC-V codes into cell specification. So this can be used for other extensions as long as RISC-V code repository has their human readable form. And also our testing tools can also be used for other extensions. So again, we can use Spike as our golden standard, or we can use RISC-V to test different extensions. And then, of course, RISC-V needs to support that particular extension. And what about semantic functions? Unfortunately, for this part, we need to write manually. And I would say for V extension, it's probably okay because they are more or less similar to P-extension. But for other extensions, then that needs to be seen. Okay, for example, the security crypto extension. So we need to encode AES into cell. And I think I know there's a way to do that, but that's very different from what we did in this work. So thank you. That's all I want to talk about our work, and I'm very happy to take your questions.
The question is a P-extension versus a V-extension, and what kind of role P could play in various applications like DSP and AI. And we actually have work in the upcoming TVN conference, use the P-extension for the post-processing like NMS in the TVN hybrid script OP. So P-extension does not load in a lot of data. It's just 64-bit and with 8-bit computation. So for small better width and have given the convolution given with the hardwire circuit, and post-processing become like bottleneck. We actually quite useful for the P-extension. Another question is, do we have the plan for the open source release? And we actually, as a PR in the GitHub, in the RISC-V cell RISC-V pull request, I think it's PR around like 132. In that request, actually we will ask audience to give more comments so we can better facilitate the software. Thank you. Bow-Yaw, do you want to enter the question for others?
Yes, I think I want to mention about this, the part about simulate compiled C code in cell. So we actually find a way to do that with some limitation, but now it's easier to do that, but not, we need to struggle with certain native C libraries and then basically put that into binary, etc. So there's a way, but not very convenient. But yes, so we can do that now. Okay, so I guess there's no further question, and thank you for your attention. And if any question, feel free to send us emails. Thank you.